Okay, Assalamualaikum, morning. Can you hear me? Okay, apa khabar semua? Sihat? Okay, Alhamdulillah. So today, before we move on to the next topic, I would like to remind on the submission of your presentation one file to Padlet, right? So make sure you upload your presentation one file by today, right? Today is the due date. If your file is too big, for example, you can alternatively upload to Elan as well, right? But you have to tell me first because by default I'll go and check on the Padlet. So if it's too big, then I'll go for the alternative, right? So you can also do on the uh, Elan system, but tell me first, okay? So that I know which one goes to Elan and the rest should be on Padlet, okay? So you guys done with it anyway? You guys done with the presentation? Dah siap ke semua? Saya dah nampak a few ada yang dah upload lah pagi tadi saya dah tengok. Alright. Okay, good Afiq. So yang mana yang dah siap boleh upload Upload dalam Padlet. Okay, that's good. You don't have to wait for the last minute. Just once ready, you just upload and leave it there. It's okay. Okay. So, alright, let's move on to our next topic, which is semiconductor heterojunction. So in the last class, we have discussed about metal semiconductor junction, where we need to know what kind of contacts do we need to put on our semiconductor to be able to extract our carriers, okay, extract our carriers from the semiconductor. And I've mentioned last time that there are a couple of types of junction, like semiconductor to semiconductor junction, metal semiconductor junction, and the other one that we're going to learn today is called semiconductor heterojunction. It's essentially semiconductor to semiconductor as well. It's just that you can, if you talk about semiconductor to semiconductor, you can actually break it down into two types, which is a homojunction or heterojunction. Right? We've learned last time all about homojunction. So homojunction is when you join your P semiconductor and N semiconductor of the same material of the same band gap, right? So the ground rule is same material, same band gap, right? So then you don't have any change in the energy levels at the junction because the materials on both types are of the same band gap and the same material, right? So today we're gonna look at heterojunction and what it is. Okay. So before we move on, let's recap a few things on what we've learned last time. So let's go to these four questions. The first one, for a semiconductor, why do we need metal contacts on semiconductor? Right. So let's discuss first. Why do we need metal contacts on semiconductor? Why? Can we survive without metal contacts? Kenapa perlu ada contacts? Anyone? Can we have no contacts? Yeah, for the carrier to flow out, right? Good, Farah. So we need to extract the carriers by having contacts. So last time we have discussed that the contacts can be generally they are metals like silver, aluminium, copper, nickel, palladium, platinum, and many more. So depending on what you need to have. And we can also use non-metal contacts like transparent conductive oxide like ITO, TiO2, tin oxide, and some other some other suitable TCOs, transparent conductive oxides, to which can also behave as a contact, right? So it's not necessarily metal, but generally, in most cases, metals are used. Okay. So let's go to the second one. What does it mean by rectifying and run non-rectifying contacts? So what is rectifying and non-rectifying? What's the difference? What's the characteristic of both? What is rectifying? Kita dah belajar tu kan diode punya properties. Rectifying, what is it? Does it flow in one direction or both directions? Yes, rectifying is Schottky contact. Just wait. Good. So rectifying um, is also called Schottky contact, and it allows only one directional current flow, right? One direction, yes. So if you're talking about non-rectifying, then it allows in both directions or ohmic contact. Okay. So draw a Venn diagram. You have to try yourself. We can't afford to draw now. So try to practice on how to draw ohmic contact and Schottky contact before joining both materials and after joining both materials. So remember the ground rule where you have to have your Fermi level on both sides aligned on the semiconductor and on the metal side, and then you have a standardized vacuum level E naught right on top. Then you need to have your work function on both cases for metal and semiconductor, where it stretches from your E naught to your EF, right? And electron affinity as well, until your EC for both sides, and so on and so forth. Barrier height and other stuff as well. Okay, so make sure you practice on how to draw the the metal contacts for both types of connection, and also make sure you know how to draw the forward bias and reverse bias condition for both metal contacts. Right, the final one, last one. Explain about tunneling barrier. So what do you understand about tunneling barrier? Is it an ohmic contact or is it a Schottky contact? Tunneling barrier. Where do you have tunneling? During Schottky or ohmic contact? Ohmic contact, right? So ohmic contact. So for you to have tunneling barrier, you have to firstly have ohmic contact. Then what else is required for you to have tunneling? Apa lagi important characteristic for your contact to have tunneling? What sort of doping level do you need to have? Yes, heavily doped, right? So you need to have heavily doped junction or heavily doped semiconductor to be able to induce formation of tunneling process or tunneling barrier. Okay, so when you dope your semiconductor to a very high level, then the depletion width will be very very narrow, and then it eases the tunneling process at a junction, right? So if you, on the other hand, if you have moderately doped or lightly doped, the possibility of having tunneling is very, very low, or maybe zero. Okay, so done with that. So now let us move on with heterojunction. Okay, probably you have seen uh this sort of junction in your presentation, right? Presentation devices. Maybe some of your devices that you are assigned with adopt heterojunction concept. So let's see and see whether your device is related or not. So firstly, what is heterojunction? So last time we've discussed that to be able to have a homojunction, we need to have the same material on both sides, and they need to have the same band gap. So the key thing is same material, same band gap, then you have homojunction. For example, if you have a crystalline silicon on N side and crystalline silicon on P side, so both of them have 1.12 electron volt, therefore they are homojunction, right? Same junction. So when you have two different materials with different band gaps, so the key thing here is a different material and different band gaps. So to form the junction, they are now called heterojunction. So if, for example, if you have crystalline silicon with amorphous silicon, they are essentially of different band gaps, 1.12 and 1.8. So they are heterojunction. uh yeah, if you combine completely different materials, of course they are heterojunction as well. For example, amorphous silicon with cadmium telluride, or crystalline silicon with zinc oxide, yeah, any completely different materials, so they are called heterojunction. Okay, so for example, if you can see here, you can see this the the picture in the middle there. So where we combine monocrystalline silicon, which is crystalline silicon, with amorphous silicon, so they are heterojunction, crystalline silicon and amorphous silicon. So therefore it is a heterojunction. 1.12 EV on the left hand side and 1.8 on the right hand side. So therefore therefore it is a heterojunction. Okay, so this one is an example of a solar cell. You can also see this from your devices that you're assigned with for your presentation one. So if you see this, this is actually a real solar cell manufactured by Panasonic. If you talk about Panasonic, we have it here in Kulim High Tech Park, Panasonic Energy, which manufactures crystalline silicon solar cell by heterojunction intrinsic technology, HIT technology, heterojunction intrinsic technology. So it's called a heat solar cell, heterojunction intrinsic technology, right? So look at the schematic representation of the solar cell. The central piece of the solar cell is made of crystalline silicon N-type, right? So the gray part here, crystalline silicon. And then if you look at the top area, you look at the top layer on the crystalline silicon is intrinsic amorphous silicon. Intrinsic amorphous silicon there. Intrinsic amorphous silicon. There is no doping. Then followed by N-type amorphous silicon. N-type amorphous silicon. Therefore, here, do you have a PN junction? Is it a PN junction here? If you see, not yet a PN junction, right? Right. So it's intrinsic and N-type, and on the front side is a TCO, transparent conductive oxide, right? Transparent conductive oxide. So at the bottom area, bottom of crystalline silicon, you can see it's intrinsic as well. It's intrinsic as well, and also P-type amorphous silicon. So do you see a PN junction there? Down there, do you see a PN junction? Is it a PN junction? Any idea? It's not a PN junction, right? Yes, it is a pin junction, correct, Farah. So it is a PIN type junction. Okay. Ada reason kenapa dia letak intrinsic kat tengah in terms of the solar cell design and stuff. So you'll probably see in your devices as well. So some of your devices adopt pin concept instead of PN junction concept, right? There's always a reason for that for your particular device. So if you look at the contact, let's relate to what we've learned before. You can see that on the top layer, you can see N-type amorphous silicon. So the H there is hydrogenated, right? H there is hydrogenated. So hydrogen ni maksudnya apa? So that means when they deposit the amorphous silicon by PECVD process, they also incorporate hydrogen. So therefore, the layer is called hydrogenated amorphous silicon, or it's called like this. It's labeled like this, ASI double dot H. So that means when the layer is deposited, hydrogen is also incorporated in the layer, right? For the purpose of surface passivation. Okay. So on top layer and at the bottom, you can see for this particular design, let's relate to what we've learned before. To be able to extract the carriers, they have TCO on the front side and TCO at the back. So transparent conductive oxide. So in this case, they use ITO, indium tin oxide. So we have learned last time that you can either have non-metal contacts, which is TCO, or you can in fact use metal contacts on your semiconductor. But in this case, Panasonic, they use metal contacts, usually silver here, metal contacts on TCO. Why do you think they use both types of contacts? Hari tu saya cakap kita boleh pakai either TCO to extract your carriers or just metal contact kan. Tapi kenapa in this case they use both types of contacts? Why do you think? Ada idea tak? Kenapa dia pakai dua-dua sekali? Kenapa tak pakai TCO saja? Any guess? Let's guess. Why is it so? Anyone? Ada idea? Tak ada idea? So, okay. In some cases where, some cases where the conductivity of your TCO is not enough, so the metal contact is also used on top of the TCO. Tapi sebenarnya kalau you tak pakai metal contact pun, by right you can just probe your positive terminal and negative terminal and do the measurement. But then if the TCO conductivity is not enough, or TCO layer is not in the optimal condition, so you may need to also use metal contact to better extract the carriers. So in this case, that's why they use both types of contact, metal and non-metal, to be able to extract the carriers from the device. Okay. So, all right, different band gaps. So energy band will have a discontinuity at the junction. So in for heterojunction, you will see later on, we will have a discontinuity at the junction. So that means you will see an abrupt change of band gap at the junction while going from the narrow band gap to wide band gap materials. Okay, may have an abrupt junction in which the semiconductor changes abruptly from narrow bandgap to wide bandgap material, as I said just now. Useful heterojunction lattice constant of the two material must be well matched. So the key here is you need to ensure good lattice matching between the two materials, because they are now of different band gaps, so they normally have different lattice parameters, so therefore they won't sit properly. So the top layer wouldn't sit properly on the bottom layer, so resulting in some dislocation. I'll show you later on, right? The lattice matching is important because any lattice mismatch can introduce dislocations resulting in interface states. So if you have dislocation, if you have lattice mismatch, you're gonna have dislocations in the lattice when you move from one material to the other material, and then this will result in interface states in the band gap. So you'll see electronic states in the band gap. There will be trap centers, recombination centers, and they will essentially be defects in the device. Okay. Right. For example, if you're talking about lattice mismatch of germanium and gallium arsenide, if you put germanium and gallium arsenide, so the lattice constant matched to within approximately 0.13%. So you need to calculate the lattice matching percentage, right? Or lattice mismatch, if you like. So on the other hand, gallium arsenide and gas or aluminum gallium arsenide junctions have also been investigated quite thoroughly. Lattice constants of them vary by no more than 0.14%. So this has to be calculated, right? So let's see how to get that. So what is lattice constant? Kita belajar kan lattice constant dalam solid state, right? Ada belajar kan? Is it? Yeah. So you dah tahu lah, lattice constant. So lattice constant or lattice parameter refers to the physical dimension of a unit cell, right? Physical dimension of unit cell. So lattice in 3 dimensions have generally 3 lattice constant referred to as A, B, C. You can see here, right? A and B and C. So before looking at lattice constant, you first have to understand whether the material has cubic, FCC or BCC or hexagonal or woodside or zinc blende or or any other, right? So for example, if you talk about silicon is a diamond with FCC. So lattice constant A is given by 5.431 angstrom. 5.431 angstrom. So the rest you can see there with different kinds of crystal structure. So how to calculate lattice mismatch? So you need to see what material do you want to deposit on what materials, right? So for example, if you want to talk about germanium and gallium arsenide, germanium here and gallium arsenide, right? So the lattice constant changes from 5653 for gallium arsenide to 5658 for germanium. If you're depositing germanium on gallium arsenide, it can be some other layers as well. So it can be gas on gas, it can be silicon germanium, silicon on germanium. It can be any combinations that's suitable for particular applications. It can be silicon on silicon carbide, right? It can be zinc oxide on silicon, right? So it can be any possible combination that we want to do for our device. So then you need to, if you're talking about germanium gallium arsenide, so you need to know you need to extract the lattice constant from the given table. Then you have to see the difference between those two material A minus B over material A, then make it percentage, and then you're gonna have your lattice mismatch, right? So how do we decide whether the material that we're gonna deposit on the underlying material is well matched or not? So if you look at this schematic representation on the right hand side, we normally have to deposit our layer on the underlying layer for various applications. For example, if you're talking about epitaxial layer, epi layer ni epitaxial layer ni biasanya kita pakai dalam LED, lasers, detectors, in which you deposit a very thin layer on a particular substrate, and that substrate can be a semiconductor material as well, or it can in fact be insulator as well. So if you're talking about semiconductor material as your underlying substrate, for example, on maybe on what gallium arsenide, or maybe gallium arsenide. So to be able to know whether they are matched or not, you need to come to this graph, right? And you need to see the lattice constants of both materials. So for example, if you're talking about germanium and gallium arsenide, so they are quite matched because their vertical position on this graph is close. So dia straight in there, maksudnya you punya lattice constant are close to each other, right? So they will form a good match. So that means the lattice mismatch calculation will result in a very small mismatch, which is good. So on the other hand, if you want to put, for example, if you want to put germanium on silicon and germanium, so you can see the mismatch is quite big because the lattice constant is different. 5.4 something to 5.6 something. That's quite a huge mismatch, right? So therefore, your device will suffer from dislocation and defects and trap states and so on, right? On the y-axis is the band gap of the materials. So lattice matching is very important. If not managed well, it will lead to dislocation and states in the band gap, right? You can see the effects illustrated on the right hand side. If the lattice is matched, if it has strain, if it's not matched at all. So when a narrow bandgap material meets a wide bandgap, so when you're combining a narrow bandgap material, which is small bandgap, and big bandgap, or narrow and wide bandgap, a heterojunction is formed. So the key here is narrow and wide bandgap, small and huge bandgaps, right? A heterojunction is formed. So your heterojunction that you get can either be one of these three situations. So it may be straddling, it may be staggered, it may be broken gap. So tengok apa yang dimaksudkan dengan all these three. So when you have your narrow band gap, EC and EV is within the wide band gaps EC and EV, so that is called straddling. Maksudnya you punya EC and EV of the narrow band gap is within the band gap of the narrow band gap material. So that's called straddling effect. So if you talk about the second case, the EC of your narrow band gap is slightly higher than the EC of the wide band gap, and the EV of your narrow band gap is within the forbidden gap of your wide band gap. So that is called staggered. And the third case is called broken gap, where your EC and EV of your narrow band gap material is completely out of the picture if you compare to the EC and EV of your wide band gap, right? This will affect the drawing of your energy band diagram. Right, for example, if you talk about NP heterojunction, right, kenapa kita tulis NP ni? Kenapa tulis NP macam ni? This small n and capital P means your n is narrow band gap and your P is wide band gap. So wide band gap kita pakai as capital. So kalau your wide band gap is n, then small p capital N, right? So in this case it's n capital P heterojunction between narrow band gap N type and wide band gap P type before contact and after contacting, right? Right, so let's look at the left diagram. So those are the band diagrams for both materials before joining each other. So just like what we learned before in metal semiconductor junction, dia punya konsep dia sama aja. So draw your E naught vacuum level, and then draw your material punya band gap, EC, EV and stuff. Work function, electron affinity, EC, EV, what else? EF, yes. Then your EG as well, EG. Then you can also label the difference as delta EC and EV, right? Narrow band gap and wide band gap. So upon joining, remember you still have to have EF align, your EF has to be aligned. So therefore, kalau EF nak align, you tengok on the left hand side, the EF for germanium is originally higher than the EF of gallium arsenide. So germanium kat atas, gallium arsenide dekat bawah. So when you join the junction, the heterojunction, your EF has to be aligned. So therefore, you're gonna have a band bending going downwards. If you go from gallium arsenide to germanium, right? Gallium arsenide to germanium. So that's why it goes down like this in order to compensate the alignment of EF here, right? So upon joining, you will see, due to the presence of delta EC and delta EV of both materials, so there'll be an abrupt junction, right? Abrupt junction. Bila nampak kat sini ada delta kat sini, and delta is here. So that is the abrupt junction, okay? Maksudnya dia tak ada continuity. So this is called the discontinuity that we discussed before. Discontinuity. Discontinuity at the junction due to the abrupt change of the band gaps when going from narrow to wide and wide to narrow. Okay, the rest remains the same. Note the potential barrier. What else? Potential barrier as well on both sides. EF alignment. Yeah, depletion width. So make sure you can draw the depletion width as well into XN and XP. So for both regions, right? So to reach thermal equilibrium where EF is aligned, just like what we learned last time when we learned about PN junction. So electrons from the narrow gap in N region and holes from the wide gap must flow across the junction. Sama macam diffusion diffusion majority carriers upon joining your p-type or n-type homojunction last time. So the moment you join them together, they're going to experience diffusion of majority carriers from one side to the other side to the other side. Then thermal equilibrium is established, similar to this heterojunction concept. So the flow creates a space charge region in the depletion width. Sama macam tadi XN and XP, you will have space charge region in the vicinity of metallurgical junction, just like last time. So on your N side, you're going to have positive charges. On your P side, you're going to have your negative charges. Sama je. So you're going to also have electric field and stuff, just like your PN junction that we learned before this. So the space charge width into the N type and P type, X and XP. So you can also label the summation of both as W. Sama, total lah. You can also sum this up as a total depletion width. Discontinuities in the conduction and valence band and the change in the vacuum level are shown in the figure. So figure tadi ya. So if you talk about heterojunction, if you talk about silicon solar cell, heterojunction, yang tadi saya tunjuk example tadi kan, heterojunction intrinsic technology, heat cell, they call it heat cell from Panasonic Energy. This is the cross section of the layers that you have. So this is the cross section. So we have monocrystalline in the center, and then we have intrinsic amorphous silicon in between. So sandwich punya concept. Then we have P and N amorphous, sandwiching. So then we have ITO, TCO on both sides, sandwich as well. And then we have silver contact on the front side or on the rear side. So kalau you tengok kat sini, dia punya PN junction is actually, the effective junction is actually at the front side, where you have your P plus, then your intrinsic, then your N layer from crystalline silicon. So that is what forms the PIN junction, right? Or PN junction lah, cuma dia ada intrinsic kat tengah. Right? So if you look at the back side, on the rear side, tak ada junction yang opposite polarity, because you have n-type and then you have intrinsic, then you have n plus. So you have n-type, then you have intrinsic, then you have n plus. So dia technically ada junction lah, but then it's not opposite polarity. It's just a junction where you have electrons and more electrons. So n-type and n plus, right? Kalau macam kat depan tadi kita ada more holes and then intrinsic, then more electrons, right? So pin junction. So this is the junction. So notice that the layer here is the silicon wafer here is 300 micron thick crystalline silicon. Yang dekat atas dengan kat bawah just a very thin layer je. So it's about 100, 200 nanometer max, right? And the band diagram is given by this. So so kiri dengan kanan is the metal, which is top metal and rear metal. So your top side is on this side, top side, because the P plus is there. So the rear side is here. Rear side is here. So tengah kat sini ya, middle kat sini. Middle region, right? So left to right, if left to right is top to bottom, okay? P plus and then intrinsic, and then you can see the abrupt junction there. Abrupt junction. Kenapa ada abrupt junction kat situ? Kenapa? Why do you have abrupt junction there? Anyone? Kenapa ada discontinuity there? Why? Kenapa? Look at the title. Why abrupt? Yes, different band gap, right? It's a different band gap because we are having transition from amorphous silicon P and N, P and I, to crystalline silicon in the middle. So this one is 1.8 EV. The center part is 1.1 EV. Then kat sini 1.8 balik. 1.8 EV, right? So it's a heterojunction on the left and on the right, or on top or at the bottom, right? So if you look at this band gap, energy band diagram, is the device at thermal equilibrium or not? If you look at the energy band diagram, is it at thermal equilibrium or not? Yes or no? Yes. Okay, yes. Why yes, Farah? Kenapa dia at thermal equilibrium? Do we have a single EF? Yes, Fermi level is aligned. Good. So sebab kita ada satu EF je kan? So if you look at your left, from your left through to the right, so we only have one EF. So we only have a single Fermi level. So it's all aligned. So that means the device is now at thermal equilibrium, right? Okay, so that's how it's drawn. So if you look at this device, it looks something like this in actual case. Cuma ni dia punya grafik lah. Tapi from the oblique maybe some degrees view on the left hand side, and on the top view on the right hand side, it looks something like this. So you can see the metal contact here. This one is metal contact. The small finger in between here, kecil-kecil ni semua metal contact. It's all silver. Ni pun silver. 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 Small line here is also silver. So in between you can see amorphous layer, N-type, P-type, just like our schematics now, right? So it looks something like this in actual case. Okay, before this, when we discuss about solar cell, you'll see more in your devices later on. When we discuss about solar cell, we normally discuss about one side illumination, right? Usually kita discuss tentang cahaya datang kat depan. Itu yang paling basic lah, paling basic physics. But in actual case, some devices particularly solar cells, some of the technologies in the solar cell, they adopt bifacial technique, bifacial cell design. Apa maksud bifacial? Maksudnya dia ada dua muka, bifacial, bukan monofacial. Yang selalu kita discuss all this while is called monofacial. Maksudnya dia ada satu muka aja. Monofacial. Maknanya dia boleh absorb light only from the top side. Tapi kalau bifacial design ni, which is a new kind of technology dalam industri lah. So, it's called bifacial technology. Okay, apa maksud dia? Maksud bifacial is light can be harvested on the front side and the light that is coming. Kalau you tengok solar panel, katalah you letak solar panel atas bumbung parking for example. Kalau you letak atas bumbung rumah atau atas bangunan, maybe tak nampak sangatlah dia punya kesan tu. Kalau you letak dekat bumbung parking kereta ke, I don't know, maybe Tesco ke, Giant ke, whatever, yang ada parking lot, dia punya parking yang berbumbung tu, kalau you letak panel kat situ, katalah panel tu belakang dia exposed to open area, so light yang reflected from the land ataupun daripada jalan, for example, katalah you ada panel kat sini, panel, for example, ni panel, so they are all mounted, for example, mounted. So the light is incident here, the light is incident here, light is incident here, but some of the light doesn't come straight on to the solar cell. So in this case, the light yang hit the surface of the road, for example, simen ke, jalan tar ke, rumput ke, tanah ke, it'll be somehow reflected somewhere. So even though it's reflected to the back of the solar cell, this concept bifacial solar cell ni dia boleh harvest from the back as well. Maknanya dia ada dua muka lah. Maknanya dia boleh harvest from the front side and also harvest from the back side. So in that case, it's called bifacial technology, right? So bifacial technology ni, it can be, if you talk about solar cell, bifacial cell ni, it can also be used as a vertical mounting. Selalu kita tengok solar panel, kita akan mount dia macam tu kan, slanted kan. So it can also be mounted vertically macam ni. It can be used as solar windows, it can be used as kalau nak mount panel macam ni, it can be used as well, because it can harvest this way and this way. It's not necessarily like this, okay, or completely flat. There are so many different configurations that we are trying to come out with to be able to harvest, all possible sources of the incident light, right? So in this case, it's called bifacial technology. This is more on industrial side lah. So sebab all this while we've learned about monofacial, satu side je. Tapi in reality, when we talk about manufacturing, technology, it can be beyond what we've learned. So kita belajar satu je kan. Tapi it can be also beyond what we've learned. So in that case, your junction will be slightly different. So that means the configuration will be slightly different. The design will be slightly different in order to accommodate bifaciality. So kita punya bifaciality tu dia punya capability lah. Right. So give another examples of heterojunction devices. So anyone working on heterojunction devices? Device yang you nak present tu, some of them are heterojunction, right? So give example. Other than solar cell, apa lagi yang pakai heterojunction concept that you've gone through in your presentation one? Okay, write an example there in the box. Right, laser. Okay, laser hetero Azrizal. So the hetero antara apa tu Azrizal? Can you share a little bit? Is it between different materials or what? It's 3-5, right? 3-5 materials, right? Alright, okay. So what? Nitride, arsenide. So other devices, ada lagi selain laser yang based on heterojunction? Do you have heterojunction in photo detectors? Ada ke? Anyone working on photo detectors? Do you have heterojunction on transistors? Ada ke BJT ke FAT ke CMOS ada pakai hetero ke? Anyone? Ada ah. So other than the lasers, ada lagi yang pakai photo detectors and other stuff. So we'll see next week when we discuss about your presentation. Okay. So yeah, I think that's all for heterojunction. A short one, semiconductor heterojunction. Alright. Nanti dekat sini you write down yourself what are the other examples of heterojunction devices other than my example in this slide. Okay. Right. So I'll guess and guess. Okay. I'll guess and guess, just like what we discussed just now. So uh, so whenever you discuss about heterojunction, so make sure you know about lattice mismatch. So what's the percentage like? So how do you calculate? So what sort of materials do normally go on other materials, right? Um, yeah, because not simply you can't simply deposit any epitaxial layer on any substrate. It won't work, right? Unless you nak dapat defects lah. Kalau you tak nak ada defects ataupun you want to minimize defects, minimize recombination, avoid the devices from not working, then you need to pay great attention to the design in terms of lattice mismatch and stuff. BJT is heterojunction. So yeah, so that means it's not only limited to optoelectronic devices. So transistor can also be heterojunction. So we'll see more. I believe more FinFET maybe, and nobody does GAA, right? Gallium, gate gate all around FET. Nobody does GAA FET. Right. Anyway, we're done with heterojunction. Don't forget to submit your presentation 1 to Padlet by today. If your file is too big, do it on eLearn and inform me as well, so that I know who goes on eLearn. And because by default I'll assume everybody goes to a Padlet. So why Padlet? Because I would like you to display your presentation, you're sharing to your other friend as well. So you can go on playing each other's file and learn from each other. You can go to the link even after the assessment finishes. You can in fact go to the link when you do your test 1, when you do test 2, sorry, do your test 2 later on if needed. So presentation 2 maybe needed as well. So we'll see how it goes. So that's the point. If you put it on eLearn, then it's just between you and me, so nobody else can access. So if you put it on Padlet, you can play each other's file, and in fact you are welcome to comment your friend's presentation as well. Just go through and see, give your thumbs up to your friends, right, for all the hard work, right? So the due is today. Don't forget, don't miss it, don't submit late. We'll have our public holiday on Monday, right? So Nuzul Quran. So there'll be no class on Monday. So we'll start our discussion on your presentation 1 on Wednesday next week, inshallah. So I'll choose maybe one file from each device. Then we'll play for about 10 minutes, and then we'll discuss in Q&A session, so where all the 3 or 4 of you will be involved on the same device, and I'll ask each of you questions and see how do we go, right? So any questions for today? All good so far? No? Any question on presentation 1? Last question before you upload your files. Don't forget to write your name and student ID, right? Your metric number. So tak ada soalan ah? Alright then, kalau tak ada soalan, thank you very much. That's it for today. I'll see you Wednesday, inshallah. Assalamualaikum. Stay home, stay safe. Bye bye.